So in this video, I want to do a quick recap of what we've seen so far, talking about second order linear homogeneous ODEs with constant coefficients. So what I want to do is I want to look at, I just kind of want to recall the process in general. So suppose that you have y double prime plus ay prime plus by equals 0. And what we're led to do is we're led to let y equals e to the rx. And when we do that, it turns out that what pops out is you have to solve a quadratic equation r squared plus ar plus b equals 0. And it turns out that there's going to be three cases. So if we have distinct roots, distinct real roots, r1 and r2, then the general solution to this differential equation, which I'll call star, then star has the general solution y equals some constant e to the r1x plus some other constant e to the r2x. So that's it. So if you have two distinct real roots, r1 and r2, then you can just take e to the r1x plus e to the r2x, put constants in front, and there's your general solution. The second scenario is that if you have one real root, and so this is a repeated root, or a root of multiplicity 2. So if you have one real root, say r0, then the general solution to our differential equation star is going to be y equals c1x plus c2 e to the r0 x. And so remember what happens is that if you can't just use e to the r0 x plus e to the r0 x because those are the same function. In particular, they're not linearly independent. So you need two linearly independent solutions. And I'm going to mention a little bit more about this at the end of this video. So we'll come back and we'll talk about this second case in just a second. But finally, if we have, in the third case, two complex roots. So if we have two complex roots, say, what do I want to use? I can't use a and b. Let me use alpha and beta. So let's say our two roots are alpha plus or minus I beta. Then the general solution to star is going to be y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. And this is a derivation that we went through last time using Euler's identity that e to the I theta is cosine of theta plus I sine of theta. Okay, so we went over that in a previous video. So these are really the three cases, and once we have this, then we can solve all second order linear ODEs with constant coefficients. But let's zoom in for a second on the second case, because I think it's worth talking about why does this behave the way it does. And I'll go through this as an example. So what I want to do is I want to consider the differential equation y double prime minus 6y prime plus 9y equals 0. So plus 9y equals 0. We know that e to the 3x is going to be some solution. So let's say that our general solution is going to be, let's just call it y equals g of x e to the 3x. So we don't exactly know what g of x is going to be, but let's say that we have g of x is just some generic function for now. And so we want to figure out what is the general solution of our differential equation going to be. And we know that the e to the 3x is there because if you look at the underlying equation r squared minus 6r plus 9 equals 0, you get 3 as your solution. Granted, it's 3 of multiplicity 2. So 3 is a solution twice, meaning that you have r minus 3 squared. So whenever I say multiplicity 2, I'm referring to that exponent. In this case, it would be r minus 3 squared, so multiplicity 2. And so let's just go through and let's compute what's y prime, what's y double prime. And for this, we'll need the product rule. So y prime is going to be g prime of x times e to the 3x plus 3 g of x e to the 3x And that means that, I guess let's actually just simplify this while we can. This is going to be g prime plus 3g e to the 3x. And then let's differentiate and find the second derivative. And we're going to get the derivative of the first. So g double prime plus 3g times the second plus the derivative of the second. So it's 3 times the first. Okay, so the e to the 3 e to the 3x was the derivative of the second term times the first. And then if we collect everything, we're going to end up with, let's see, we're going to end up with g double prime plus 3g prime plus 3g prime is plus 6 g prime of x, and then plus our g of x term is going to be 9 g of x. And that's e to the 3x. And now let's plug everything in. So now let's just plug in our expressions for y double prime into the y double prime. We'll plug in our expression for y prime into y prime, and then we'll plug in our expression for y into y. So this means that our ODE, let me call this star 2. So star 2 is going to become the following. So that means that we're looking at y double prime. Let's just go back so I can read it. Y double prime. So that was g prime of x plus 6g prime plus 9g of x times e to the 3x. So that's our y double prime minus 6 times y prime. So that's 6 times g prime plus 3g e to the 3x plus 9 times y, which was g of x e to the 3x, and that's all going to be equal to 0. Okay, so I had to do that on 2 lines there, but that's the idea. And then notice that you can factor out an e to the x on the left side, and then you can just divide everything by e to the 3x. So we might as well just cancel the e to the 3x's right away. You can just divide both sides by e to the 3x, and the right side is just 0. So 0 divided by whatever is still 0. So we end up with g double prime of x plus 6g prime plus 9g minus 6g prime. So just distributing through minus 6g prime minus 18g plus 9g of x is equal to 0. And then what happens here is that you'll have 9g of x minus 18g of x all add up to 0. 6g prime minus 6g prime adds up to 0. And so this means that g double prime of x is 0. And therefore g prime of x is constant. So we'll call it C1. And g of x is linear, which is C1x plus C2. So this is a straightforward calculation. Nothing mysterious happened. But this does explain why the general solution, when you have a repeated root, is exactly C1x plus C2 e to the 3x. Or if you want to think about it, you can have C1, so you'd have a constant, so you'd have a constant times x e to the 3x plus just another constant times e to the 3x. Okay, so maybe that's a slightly easier way to think about it, but same thing. Okay, and so that's the general overview of second order linear homogeneous ODEs with constant coefficients.